So quantum mechanical theory describes the behavior of electrons. Electrons in atoms exist within orbitals, those funky balloon shapes we just looked at. A description of which orbitals are occupied by electrons is called an electron configuration. And you should have heard of this and done a little bit of this in your previous chemistry class. So electron configuration. So for hydrogen only has one electron, and so that electron will be in the lowest energy orbital. So it'll be in the principal quantum number 1, the first energy level, in the only orbital there, S, and there's one electron in there. So this tells us which orbital we're talking about. This is the principal energy or principal quantum number, and this is how many electrons are there. So when you look at hydrogen's one electron, you see that it's going to occupy the lowest energy orbital in the hydrogen atom. And this fits with pretty much everything else we've observed in nature, where things tend towards the lowest energy. Balls roll down the hill, they don't roll up the hill, because when they roll down, they lower their potential energy. Schrodinger's equation for multi-electron atoms can't be solved exactly. And it's more than one electron makes things really, really complicated because there's electron-electron interactions. So two things that we will consider in multi-electron in multi-electron atoms. The two things we'll consider in multi-electron atoms are electron spin and energy splitting of sublevels. So there are electron configurations and there are orbital diagrams. And as the name suggests, a diagram is more like a picture, right? So for hydrogen, the electron configuration is 1s1. This is the orbital diagram. So it's going to represent each orbital as a box, and it's going to represent the electrons as half arrows. Electrons have spin. We talked about that. That's that final quantum number. Can be plus 1/2 or minus 1/2. And we can think of it as being like a top spinning clockwise or counterclockwise, right? One or the other. If you look at a group of hydrogen atoms, about half of them will have their electrons with a positive spin and half with a negative spin. And it's just convention that pointing up is positive. It just kind of made the most sense. The Pauli exclusion principle tells us that no two electrons in an atom can have the exact same 4 quantum numbers. So it's like no two people in the United States can have the same social security number, right? It has to be unique to you. You're the only one with your social security number. So if we have electrons in the same orbital, like in that 1s orbital, the first 3 quantum numbers are the same. And so it's the last quantum number that makes that set of numbers individual. One will be plus 1/2 and one will be minus 1/2. So in an orbital, we can have a maximum of 2 electrons, and they're going to have opposite spins. That's nice. So helium has 2 electrons. So this would be its electron configuration. The 1s orbital has 2 electrons in it. And here's the orbital diagram. We have to have one with a positive spin and one with a negative spin. So one arrow is going up and one arrow is going down. And these are the sets of quantum numbers for those 2 electrons. They both are in principal energy level 1 in an s orbital. There's only one orientation for that, and this is where they become different. One's up and one's down. So each electron in an atom has its own set of 4 quantum numbers. So the sublevels, which are designated by the second quantum number, and we typically refer to as SPD and F. The sublevels in hydrogen all have the same energy. So the energy only depends on what the principal quantum number is. So we say that they are degenerate. So degenerate just means they have the same energy. But when we have more than one electron in there, things get complicated, and the energy levels are not what we would necessarily expect. They are not degenerate. So we have charge interactions, we have shielding and penetration, and these all affect the energy of those different sublevels. In general, though, the lower the value of L within a principal level, the lower the energy of the orbital. So say you were looking at principal energy level 5, the S sublevel is going to be lower in energy, and P is going to be more, and D is going to be more, and F is going to be more. And we also need to talk about Coulomb's law. So this is a mathematical illustration of Coulomb's law. And what we need is E is proportional to the charge on one thing times the charge on the other thing divided by the distance between them. So the potential energy, E, of two charged particles depends on their charges and their separation. If both of these particles are positively charged, then the potential energy is positive, meaning it's not stable, and those particles are repelled by each other. If they are of opposite charge, one's positive, one's negative, then the potential energy is negative, it's more stable, and they will be attracted to each other. As R gets smaller, the distance between them, as R gets smaller, the attraction or the repulsion gets larger. So if we think about refrigerator magnets and pieces of paper that you're sticking on the refrigerator. So Q1 might be the strength of the magnet, and Q2 is, how magnetic the surface of your refrigerator is. And then R is the distance between the magnet and your refrigerator. If you put one piece of paper between them, the magnet's probably going to hold up one piece of paper. Otherwise, it's probably not a very good magnet. You should just get rid of it. But put two pieces of paper, 3, 4, 5. At some point, the papers are going to start sliding down, right? The magnet doesn't hold them up anymore. Why? Because R has gotten bigger, and so the energy, the potential energy attracting them is smaller, and gravity is taking over. Okay? So we get attraction between the positively charged nucleus and the negatively charged electrons. Coulomb's law, Q1, Q2. One's positive, one's negative. But then we also have repulsion by negatively charged electrons with each other. So they're going to repel each other. So those other electrons, in a sense, shield the nucleus. So as another electron is looking at the nucleus, there's these electrons in the way, and they sort of subtract from the positive charge. It's not as attractive because it's shielded by these other electrons. So the total amount of attraction that an electron feels or sees for the nucleus is called the effective nuclear charge, ZF. So the effective nuclear charge is dealing with Q1, Q2. If that's bigger, there's more attraction. If those are smaller, there's less attraction. And then as an electron gets closer to the nucleus, R gets smaller, and so the attraction also increases. Well, there are other orbitals with other electrons in there. And so the outer electron is said to penetrate the electron cloud of the inner electrons. And if it can penetrate in and get closer to the nucleus, it will experience a greater interaction, a greater attraction. So the degree of penetration is related to the orbital's radial distribution function. Now that probably made very little sense. It's okay. So this one over here is about shielding. So this would be lithium, element number 3. 3 protons in the nucleus, 3 electrons. And so these first 2 electrons are in the 1s orbital, and this one is going to be in the second principal level, the 2. So this one's going to be further away, and as it looks at the nucleus, these guys are a standing wave around the nucleus, right? And so as it looks at the nucleus, it kind of sees the charge, the actual charge on the nucleus, minus the number of electrons that are closer to it. And so it's going to see an effective nuclear charge of +1. So this electron is attracted to this nucleus the same as if this was a +1 nucleus without any other electrons getting in the way. Does that make any sense? Do you want a really weird analogy? Okay. It's weird. So think about people on the beach, right? And, just say you've got this person who's got this really awesome body, and, they're just wearing, like, a very, very skimpy bathing suit, right? You can see almost everything, right? You're like, ooh, really attracted to them. Well, what if they put on a parka and boots and a face mask like they were going to go out in the snow in Alaska? Can you even really see them anymore? No. Are you going to be as attracted to them? No. So these electrons that are closer to the nucleus are like layers of clothing, right? And they're getting between you and this beautiful person that you're interested in. The train likes it. So that's shielding. Penetration over here is if that electron that's out here has a radial distribution function that allows it to come in closer to the nucleus, then it's going to have greater attraction for the nucleus, because maybe, this person likes you back and they're like opening their parka and saying, hey, come on in, let's snuggle up together. I don't know. That's new. That's a little too weird, maybe. I never know what's going to happen. So how does that penetration occur? So here we have those radial distribution functions. So here's the 1s orbital. It's off the chart, but it goes way up and down. And so this shaded region here is where the electrons in the 1s orbital are. The 2s orbital has a bit of a node here, and then it has a bunch over here, right? And so this is said to be penetrating into the 1s orbital. Part of the 2s orbital is actually in the same space as the 1s orbital. And then the 2p orbital doesn't have a node, and it's going to be like this, and it's also penetrating into the 1s space. But the 2s orbital here gets a lot closer, right? So here they're the same, but here the 2s is closer to the nucleus. So what that means is that these p electrons are more shielded from the attractiveness of the nucleus, and so they're going to be higher in energy, and the 2s electrons will be lower in energy because they're able to get closer to the nucleus and experience its positive charge. Any questions? So because of how those sublevels penetrate each other, the sublevels in a given principal energy level are not degenerate. And then when we get further up into the 4th and 5th principal levels, the effective penetration is so important that we actually have the 4s orbital being lower in energy than the 3d orbital. And things get all messed up. But I'm going to show you how it's all, that order is all hiding on the periodic table. We don't need to memorize anything. As we get beyond the 4s, then we get that the energy separations between the different sets of orbitals getting smaller and smaller and smaller, and we can actually get different energy ordering in different elements. And we're not going to worry about that. We're going to stick with the smaller things. Okay, so this is looking at the different orbitals. Here, each orbital is represented by a line. So this is the 1s sublevel. There's one orbital. The 2s sublevel, one orbital. This is higher in energy. The 2p sublevel has 3 orbitals, right? And these are higher in energy than the 2s orbital because the 2s orbital sneaks in and penetrates into the 1s and gets a little closer to the nucleus, which lowers its energy. Then we have 3s and 3p, and this is where things kind of get wonky. The 4s is actually lower in energy than the 3d. And then it goes 4p and 4d and 5s and yikes after that. Okay? So coming up is a slide about the quantum hotel for electrons. But this is, I mentioned it to you last week. So this is that wonky looking hotel. And these are the floors. Right? So the first floor, there's 1 sublevel. The second floor, 2 sublevels. Third floor, oops, I missed. That one's up here. 3 sublevels. The fourth floor has 4 sublevels. The F isn't shown. And so in this analogy, you know, the further away from the busy lobby you are, the more expensive the rooms are. You could say, well, you got a better view out the windows or something. And I think of this as being like the elevator, and elevator where the ice machine can get kind of noisy, people getting rowdy at night. And so the further down the hall you are from the elevator, the quieter it is and the more expensive the rooms are. Make sense? So we talked about the Pauli exclusion principle, and there's another principle called the Aufbau principle. So electrons are going to occupy these orbitals in a way to minimize the energy of the atom, which means that the lower energy orbitals will fill first, and then the higher energy orbitals. So electrons are cheapskates. They want to stay at this place, but they want to spend as little money as possible, so they're going to fill up all the cheap rooms first, right? Oops. If we look at orbitals in the same sublevel, in the hotel analogy, this is beds in the same room. They all have the same energy. They have the same cost. So there's this room and it's got 3 beds in it, and they're going to charge you to stay in the room. It doesn't matter what bed you sleep in, the price is the same, right? Because how are they going to know what bed you're sleeping in? This is the filling order, but again, I'm going to show you how you can find that on the periodic table. Orbitals can hold no more than 2 electrons each. So in the hotel, you can only have 2 people in a bed. Pauli exclusion principle says that the spins are opposite. So I had to get a little creative with this one. This was inspired by a trip to Fort Snelling, Minnesota, where the soldier barracks had these really narrow bunk beds. So if you think of a bunk bed, we'll just look at the bottom bunk. So they were narrow, and 2 soldiers slept in those. It was more narrow than a twin bed, right? It was really skinny, and you're like, how the heck could 2 people even fit in there, and then why? Well, it was to share body heat and keep each other warm because they didn't have furnaces It was stinking cold in Minnesota, and they're basically in a log cabin, right? So what they did is one guy would sleep with his head that way, and the other guy would sleep upside down. Because, you know, your shoulders are kind of wide, right? And so this way, two people could take up less space in the bed. You can try that at home if you want to. So with the electrons in this hotel, what I'm saying is one sleeps right side up in the bed and one sleeps upside down in the bed. I'm not sure why, but I think of electrons as being male, which reminds me of my kids when they were in high school and went on choir trips. So, you know, here's 4 high school guys in a hotel room with 2 double beds. Where do they sleep? One guy in each bed, right? And 2 on the floor, or 1 in the bathtub, right? Because they don't want to touch each other, right? When they're sleeping, that would just be so gross. So here you cannot sleep on the floor because the floor is lava, okay? You have to sleep in the bed. And so they sleep opposite of each other just to avoid any appearance of anything. I don't know if you're having a dream about your girlfriend or your significant other and you tried to kiss the guy, you'd get his feet and you would fail. I don't know. You can jazz it up however you want. So that's the Pauli exclusion principle. The spins have to be opposite. And then there's Hund's rule that says when you're filling degenerate orbitals with the same energy, electrons will fill them singly first with parallel spins. So this is a p sublevel with 3 orbitals. There's 3 beds, and the electrons are going to come and fill them in. The first guy's going to take the one closest to the door, and he's going to, of course, sleep right side up in the bed. And the next guy's going to come in, and he's got a choice. I could share a bed with that guy, or I could have my own bed. What's he going to do? He's going to take his own bed. Who wouldn't? And the third guy comes in, he's going to take his own bed. So we're filling these singly, 1 electron per orbital, and they're going to have parallel spins. Just by convention, the first one's always pointing up. Now, a 4th electron comes in. He would prefer to sleep on the floor, but the floor is lava. You can't do that, and so he's going to sleep upside down in this bed. That make sense? So, you know, obviously the hotel analogy helps us to understand these ordering principles, and some of this other stuff is obviously not at all what they're doing inside of an atom, right? Okay, so here's the key, the correlation for the quantum hotel, a discount resort for electrons in Mrs. K's chemistry land. Chemistry land is this imaginary place in my mind where all sorts of fun chemistry thing happens. So the first floor has 1 room, that's the S sublevel. Second floor has 2 rooms, S and P sublevel, right? Third floor, 3. Fourth floor, 4. So each S room has 1 bed. The P rooms have 3 beds, the D rooms have 5 beds, the F rooms have 7 beds, right? It's odd numbers, 1, 3, 5, 7. If there was another one, it would be 9. You can only have 2 people per bed, must have opposite spins. They're going to sleep upside down. So the floor of the hotel is the principal shell. The room is the subshell. Each bed is an orbital, a person is an electron, and money is energy. So it's a discount resort, right? So these electrons are going to want to go to the cheapest rooms first. Okay? Any questions? So here's our first floor of the hotel. Here's the second floor. These are more expensive rooms. And then we've got this one on the 3rd floor, and those are more expensive. This one's more expensive, and then this one is more expensive. But this 4S room is cheaper than the 3D room. Sometimes pricing in hotels doesn't make a whole lot of sense, right? But you could maybe rationalize, well, this one's so much closer to the elevator It's kind of loud there, and so that's why that one's more expensive. I don't know, make up what you want. So electron configurations, unless we say they're for some particular excited state, electron configurations refer to the ground state, the lowest energy electron configurations. And so in the hotel, an electron configuration is like the guy at the front desk. He has a log, and he keeps track of where all the electrons are, so that if another electron comes in, he can send him to the correct room. So this is just a list of where the electrons are staying. So in a neutral atom, the number of electrons is equal to its atomic number, right? So nitrogen is number 7. That means it has 7 electrons. So how does this 2 electrons in one orbital thing work? Because they're both negatively charged, and don't they repulse each other? Well, they do, but that's where their spin comes in. So if they have parallel spins in different orbitals, that minimizes the repulsion. When an electron, 2 electrons occupy the same orbital, they're even closer, and they're going to have opposite spins to coexist. So here's a bigger electron configuration. This is for krypton, 36 electrons. So there's 2 electrons in 1s, 2 electrons in 2s, 6 electrons in 2p, 3 in 2s, 6 in 3p, 2 in 4s, 10 in 3d, 6 in 4p. So this means that the 4p room has 6 electrons in it. Okay? It could have 14, so it's not even half full yet. Well, that gets a bit long and tedious, especially when you get to things like silver or something with even more electrons. So there's a shorthand method. It's called the inner electron configuration, or the noble gas configuration. I usually refer to it as the noble gas shorthand. And so what we do here is we look at the previous noble gas, and we substitute for that. So here we've got krypton was up to 4p6, right? So that highlighted part, that is the electron configuration of krypton. And it's always going to be the same, right? So instead of writing all of that out, we're just going to write the element symbol for krypton and put brackets around it. And we understand that this means the electron configuration of krypton and then 5s1. There's just one more electron for rubidium. It's a lot shorter. You can only do this with the noble gases, okay? You can't say for krypton, well, krypton is bromine in brackets and then one more electron. You can't do that. We're just looking at the ends of the rows, okay? So we looked at hydrogen and helium. Here's lithium, beryllium, boron, and carbon. So this is how we usually draw orbital diagrams, is just, on a single line, because if we drew like these big things, it doesn't fit very well. So here we're putting them in order of increasing energy or increasing cost. And so this is a room, and that's a room, and this whole piece here is a room. Each of the squares is a bed, okay? So for lithium, one electron comes in, and the second one's going to sleep upside down, and then the third one is going to go over there. Let's see if this works. And so for beryllium, it's going to first go here and then upside down. Then the second one's going to have to pay more for the room, go to the more expensive room, and then this guy's going to go upside down. So they're not going to go up to a more expensive place unless they have to. So for boron, this all is happening the same way. The first room, the second room, and now we're getting into the 2p room, the p room on the second floor. There's just one electron there, so he's going to just take the first bed. Here it's like that, but we've just added one more electron. There's 1, 2, 3, 4, 5, 6. That guy is going to take his own bed because he can. You guys ever ride the bus? So you get on the bus, and there's an empty seat, and there's a bunch of seats with one person sitting in them. You're going to go sit with a stranger? No, that's not good bus etiquette. You're going to take the empty one, right? They're all going to fill up with one person, half full, and then you get on the bus, and there's no empty seats. Now it's okay to sit next to a stranger, right? Same thing here. Okay, write the orbital diagram for argon and determine the number of unpaired electrons. So the first thing to do here is to figure out how many electrons are we dealing with. How many electrons does argon have? 18 electrons. It is element number 18. So I'm going to just draw some orbitals here. So that's going to be 1s, and this will be 2s, and next will be 2p. And then we'll go up to the third floor, 3s, and then the 3p room. So what we're going to do is we're going to stick those electrons into their beds. So we're going to start with the least expensive room, the lowest energy orbital. We're going to put one electron with a positive spin and up arrow first. If there's not another equally priced bed, we're going to pair up before we go up to the next expensive. So we'll count 1, 2, 3, 4, 5. Next guy's going to take his own bed. 6, 7. Now, number 8, they're really stingy. Not going to pay extra for this more expensive room. He's going to sleep upside down next to this guy. So what did I say? That was 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's the orbital diagram for argon. What do we mean by unpaired electrons? Electrons that have a bed to themselves. They're not sleeping with another electron. Are there any unpaired electrons? No, 0 unpaired electrons. 0 unpaired electrons. From this, we could very easily write the electron configuration. This is a shorthand that the guy at the front desk uses. So 1s, how many electrons are in there? There's 2. And the 2s has 2, and the 2p has 6. And the 3s has 2, and the 3p has 6. If I add up these superscripts, they should add up to the number of electrons. Any questions?